Okay, welcome. In this video, we are going to revisit our discussion of Bootstrap confidence intervals, which we introduced in the context of for loops in the previous module. But we'll see how we can use apply functions to come up with an algorithm for generating a Bootstrap distribution using the chicken weights data set that we just explored in the previous video. So we're going to work with this data frame called chick weights. This is in base R, so I think it's in like the data sets package that should already be installed and loaded. So if you run summary chick weights, you should see a summary of the data frame. It has two variables, weight and feed. So it's calculating the weight of chickens 6 weeks after they were born, based on which feed they received over the course of their life so far. So the chicks were split up into different feed groups. They received just one type of feed, and then they recorded their weights 6 weeks later. Okay, so maybe what we're interested in doing, rather than thinking about what happens with the chicks that receive different types of food, but if we think about them all grouped together, like what is the average weight of all 6-week-old chicks? Well, we've got a sample of 71 chicks. And from our sample of 71 chicks, what would be a good estimate for the mean weight of all chicks at 6 weeks? So we could take our sample of 71 observations. We see that the mean is 261.3 grams. If my sample was picked randomly, then I should expect that the characteristics of my sample should resemble the characteristics of the population, and probably the population mean is somewhere around 261 plus or minus some margin of error. And so we can use bootstrapping and bootstrap distributions to figure out what is a reasonable margin of error to build into our estimate. And so we did take a look at that concept in much more detail in the previous module. But we can set up confidence intervals are the most commonly used interval estimate. And there are some situations where we know what the population is from which we're sampling, and we can use theoretical models to come up with a theoretical description of the sampling distribution. In this situation, we don't know the population. That's the whole point, is I don't know what the mean of the population is. So I cannot use something like a central limit theorem necessarily to help me here. But a bootstrap confidence interval we can use when the population distribution is unknown, and we can use bootstrapping as a method for approximating the sampling distribution. And once I have a sampling distribution, we can then use the standard error of that sampling distribution, which is the standard error, to build in a margin of error into our estimate. But how bootstrapping works is we have a sample of n values that we've randomly selected from the population. We'll call those values x1 up to xn. Then we've got some parameter that we want to estimate from the population. For example, like what is the mean of the population that we denote with the Greek mu. We think of a natural estimator for that parameter. In the case of the population mean, we would probably use a sample mean, x bar, as a reasonable unbiased estimator for mu. And then we bootstrap. So then I take my sample, I generate a bootstrap resample by picking at random with replacement from the original sample. Each time we pick a bootstrap resample, we're going to calculate a sample statistic from that bootstrap resample, which we would use to estimate the population parameter. We repeat this many, many times, like 10,000 times, over and over and over again. And then we look at the distribution of bootstrap statistics. And then we pull off quantiles from that bootstrap distribution. And again, if you're not familiar with this, I would encourage you to go back to the previous module where this was discussed in a little bit more detail. But that's the process that we want to implement here. So let's think about, first of all, how we can set up the Bootstrap sample. And then we'll go into the next video. We'll talk about how we can use apply functions to repeatedly pick bootstraps and calculate statistics from those bootstrap resamples. But we're going to work with just the weight of the chicken. So we're not going to worry about the feed variable now in our analysis. We're going to group all of those chickens together. So I'm going to store the data to a vector that I'm calling WT. And we can print that out. So this is a vector that contains 71 observations. We can see all of the weights of all 71 chicks in our data frame. These are their weights in grams in 6 weeks after they were born. So how bootstrapping would work is I would take this sample and pick with replacement a sample that has the same size. So we can use the sample function to sample values from the vector weights. That would be all of these values. And we're going to generate a sample that has the same number of values as the original sample. So the size of the original sample we can calculate with the length function. And then whenever we're bootstrapping, we are picking with replacement. So the default is to not sample with replacement when you use the sample function. We want to override that default. So we're going to set the replace argument to true. And I put parentheses around this command since I want to see the resulting output. So here I've got a bootstrap resample. It consists of 71 values that were picked with replacement from the original sample. And every time I run this command, since I haven't set the seed, we get a slightly different sample. So what bootstrapping would look like is we pick the sample, we calculate the mean, we pick another sample, we calculate its mean, we pick another sample, we calculate its mean, and then we want to look at the distribution of all of these bootstrap means. And we can look at the variability in those values to think about what is a reasonable amount of uncertainty to build into our interval estimate. But we'll create this simulation using an apply function in the next video.